Hello everyone, welcome to the next lesson in this grade 11 physics class. So we're looking at magnetism and the electromagnetic field now, really electromagnetism in the end. So in my in-person class, I usually have this little demonstration all set up and ready to go, where there's magnetic levitation going on. Let me just type in magnetic levitation here and go with. So I would just have this little demo going. So it's a little spinning top, and there's 3 magnetic poles, and so it's just sitting in a magnetic potential well. Here's the lingo. But yeah, you can see it's just spinning away. It's actually spinning really fast. You can't really tell, I guess, but there's no strings attached. So it's just a neat little high interest intro to magnetism, getting us thinking about magnetism. And then I quickly pull away from magnetism itself for a bit and start to talk about electromagnetism, trying to tie the two of them together, of course, right? So in 1820, Christian Ørsted discovered electromagnetism by accident. He had electricity flowing in wires, had compasses nearby, and he found that there were, where is it here? Found that a compass needle would be deflected by electricity flowing through a wire. And so see here, if you have the compass lined up with the wire, as soon as you attach the 9-volt battery, connect the circuit, that the field deflects sideways. And so for now, it's all we're looking at is just that there's a connection between the two. There's a connection between electricity and magnetism. And in the next lesson, we'll learn more about why that is. All right, and we're leading towards that, I guess. But yeah, we'll look at the exact magnetic field produced by the current carrying conductor and why the needle moved the way it did, what direction it wanted to point, and so on. So electromagnetic fields. First, let's talk about gravitational fields. And so if we're looking at gravitational fields, we know there's like a force of attraction of masses all around this. And so we say, oh, there's a gravitational field. We say there's a gravitational field. There must be because there's forces around it, right? So basically the existence of those forces shows that the gravitational field exists. And, you know, that seems familiar to us, even though gravity is actually less understood than any of the fields. But it's just everyday experience, right? And so very similar with electrostatic or electric fields, at least. You've got attractions of negatives to a positive. So again, there's an electric field, and you got repulsions as well as that sort of that new part, right? So electric fields are a little bit different than just gravitational fields because you can have repulsion as well. So this observation connected electricity and magnetism. And so jump to say here now that we have this electric and magnetic field intertwined, you know, has a bit of a, you know, you can see that this is how this could be true, right? If you have electricity flowing, you have a magnetic field associated with it and vice versa. Okay, so you have the electromagnetic fields, it turns out, has 2 parts. It has a magnetic field and an electric field. And so they are at 90 degrees to one another. You'll see the 90 degrees come up in our analysis of things soon. The speed of these electromagnetic waves is, of course, the speed of light, because light really is an electromagnetic wave. So that's illustrating the idea of you have either a magnet or electrostatic. There's basically a vibration or a ripple, and that ripple goes out in the electromagnetic field as an electromagnetic wave. That's just another diagram of it. And so if you think back to, we started talking about gravity, right, as a way to introduce this. In past lessons, several years ago, 10 years ago now, I guess, I wrote, you know, this, we should be able to find gravity waves, right? Since we have gravity, a fluctuation in gravity, like if this were, you know, jiggle back and forth, then it would send out a ripple in the gravitational field. And so this is something you could look for, you know, get a PhD in and so on. And of course, they have since discovered gravity waves. So it's kind of exciting for me to be teaching in a time period where there's a major discovery like this that, you know, was predictable based on things. People, I never really heard someone talk about gravity waves before that. So I just was basically making that connection, and then sure enough, it ends up getting actually discovered, which is pretty cool. And so the other thing we've talked about already was in this semester was the idea of fields and the idea of action at a distance and exchange particles. And so with the strong nuclear force, we have the gluons, and that's like tried and true, very, very well understood, a great set of equations that describes things perfectly, super predictable, super consistent, no flaws found by anyone anywhere. Same thing for electromagnetism. Okay, the exchange particles, photons, and again, an incredible, robust set of equations that describe this, the Maxwell's equations, they're called. And then again, the same thing for the weak nuclear force, super well understood, very predictable. We have equations that represent things, equations that predict things, and so on. We have yet, this is when I was talking about gravity being sort of familiar to us, we can use it as a feel-good introduction, but the strange thing about gravity is it's really not well understood at the fundamental level. So we have not, scientists have not, physicists have not been able to find a nice set of equations that describe gravity in terms of exchange particles as a regular field action at a distance kind of force would have. And not only that, but the actual gluons and photons and bosons, those are all experimentally confirmed as well. So the graviton, the alleged, supposed, whatever exchange particle for gravity, can't be found yet. No one's managed to find it, even though they had experiments where they thought, geez, if it exists, we should be able to find it. We also don't have a nice set of equations like the standard model of physics, the quantum chromodynamics, the Maxwell's equations, quantum electrodynamics, all these different formulas and sets of equations that describe these things. They'd like to find that for gravity, but they haven't been able to. I'm beginning to think that maybe it's because it's not a real force, as we looked at in those previous videos, right? So it might be a dead end, really. Like there might not be a set of equations like that for gravity. It might not be how it is. We just feel gravitational force when we're in the presence of gravity, when we're in a gravitational field. So then begs the question of like, okay, what's the difference between a gravitational field and these other fields then, if they have exchange particles and gravity doesn't, and so on. So big area of research yet to be followed out, basically. Now, that's getting into complicated stuff, but the main reason of talking about that is just to make it obvious that the source of magnetism, right, vibrations in an electromagnetic field, right, causing the magnetic portion of this thing, so the purple part, right, you have magnetism, you've got a magnetic field going on, all the two are intertwined, and so it should be pretty obvious at this point that we're talking about electrons as being the source. So you look at the atom, of course, you've got electrons that can orbit around and cause there to be a magnetic field, and so this is what causes magnetism. And so the first kind of hand rule to do with describing the connection between electricity and magnetism would be your left-hand rule for electrons. So there's an L in each of those, and we're going to talk about a right-hand rule as well soon. So that's why I'm emphasizing that. So your electron based left-hand rule, both with L's. If you curl your fingers in the direction of the electron flow, then your thumb points in the direction of magnetic north. Right? Everybody's left hand would do the same thing. So it's your little tool as part of your body that helps you identify magnetic field directions. Okay, so that's like each atom having that magnetic field associated with it. So magnets and how do they work? Let's watch a little video here. Hope I don't get copyright. So shout out to Minute Physics. I give credit. I'm not stealing. I'm just sharing. There we go. So.
If you take a piece of wood and put it next to another piece of wood, nothing happens. And if you take a piece of granite and put it next to another rock, still nothing. But if you take this piece of iron and put it next to this other piece of iron, magnet. Magnetic objects are able to magically attract at long distances because they generate magnetic fields that extend invisibly out beyond the object. But the mystery is this: where do magnetic fields come from?
Well, that's easy, Henry. We've known for a long time that electricity and magnetism are really just two sides of the same coin, kind of like mass and energy or time and space. They can be transformed into one another. And in fact, a magnetic field is just what an electric field becomes when an electrically charged object starts moving.
That makes sense for explaining why a current of electrons flowing through a wire causes this compass needle to move, or how currents in the Earth's outer core generate the geomagnetic field. But a bar magnet or the compass needle itself are just pieces of metal without any electrical current running through them.
Or are they? At the microscopic level, there are loads of electrons whizzing around the atoms and molecules that make up any solid.
Right. This brings up an excellent point. The magnetic behavior of any everyday object is influenced by a fascinating combination of effects ranging from the level of particles to atoms, collections of atoms, and collections of atoms. First, individual particles. Unlike the everyday workings of gravity and electricity, permanent magnets can only be fully understood as a quantum mechanical effect. In much the same way that particles like electrons and quarks have fundamental properties called mass and electrical charge, most particles also have another intrinsic property called tiny magnet. Just kidding, it's called intrinsic magnetic moment. But really, that's just technical mumbo-jumbo saying that particles with electric charge also happen to be tiny magnets.
If you want to know why they're tiny magnets, well, you may as well ask, why are particles charged in the first place? Or why do objects with mass and energy attract each other gravitationally? No one knows. We just know that's the way the universe works.
Exactly. And since the night.
So basically, there's some things where you can just observe it and say, well, that's what's happening. And then we end up developing a set of equations that help us work with it and then calculate values predictably and so on. And so then we have a feeling that we understand it. But really, it's a model of an observation, right?
1920s, we've known that each individual electron or proton is basically a tiny magnet, which brings us to the level of atoms. An atom is a bunch of positively charged protons with a bunch of negatively charged electrons whizzing around them. The proton tiny magnets are about 1,000 times weaker than the electron ones, so the nucleus of the atom has almost no effect on the magnetism of the atom as a whole.
And you might think that since many, though not all, of the electrons are also moving, that like a current in a wire, they should generate magnetic fields due to that motion. And indeed they do. These are called orbital magnetic fields.
Except these don't usually contribute to the magnetic field of an atom. Here's why. Electrons in atoms are accurately and complicatedly described by quantum mechanics, but the gist of the story is that electrons congregate in shells around the nucleus. The electrons in any filled shell zoom equally in all directions, so the currents they generate cancel out and generate no magnetic field.
Right, 2 electrons in the first shell, beta, they have even numbers and they go in opposite directions, so they all cancel out.
These electrons also come in pairs whose tiny magnets point in opposite directions and also cancel. However, in a half-filled shell, all of the electrons are unpaired and their tiny magnets point in the same direction and add up, meaning that it's the intrinsic magnetism of the electrons in the outer shell that gives an atom the majority of its magnetic field. So atoms near the side of any of the major blocks of the periodic table, which have full or nearly full outer electron shells, aren't magnetic. And atoms in the middle of the blocks have half-full outer electron shells and are magnetic. For example, nickel, cobalt, iron, manganese, chromium, etc.
Wait, but chromium isn't magnetic.
But just because an atom is magnetic doesn't mean that a material made up of lots of that atom will be magnetic, which brings us to the level of crystals. When a bunch of magnetic atoms get together to make a solid, they generally have 2 options. One is for all the atoms to align their magnetic fields with each other, or they can align their magnetic fields in an alternating fashion so they all cancel out. The atoms will do whichever one requires less energy.
That's why chromium, for example, is a very magnetic atom, but a very unmagnetic solid, because it's one of the most anti-ferromagnetic materials that we know. Iron, on the other hand, is the namesake of ferromagnetism, so it is unsurprisingly ferromagnetic, or in usual parlance, magnetic.
Sometimes. The last and final level of magnetism is that of domains. Essentially, even in a magnetic material where the magnetic fields of atoms line up together, it's possible that one chunk of the material will have all its atoms lined up pointing one way, and another chunk will have all its atoms pointing another way, and so on.
All of these domains are of a similar size. Then none may be strong enough to force the others to align with it. In which case, a piece of iron, for example, may have no magnetic field at all because of all the warring magnetic kingdoms within it.
However, if you apply a strong enough magnetic field from outside the material, you can help one domain expand its control over its neighbors, and so on, until all of the domains have been unified into one kingdom, all pointing in the same direction.
And now, finally, you can rule with an iron fist. I mean, magnet. It's magnetic because it's ferromagnetic and all of the domains are aligned.
Exactly. What's remarkable is that magnetism is a fundamentally quantum property amplified to the size of everyday objects. Every permanent magnet is a reminder that quantum mechanics underlies our universe. In order for an everyday object to be magnetic, though, it has to have a unified kingdom of magnetic domains, each made up of bajillions of magnetic atoms, which also need to be aligned with each other, each of which can only be magnetic in the first place if it has an approximately half-filled outer shell of electrons, so their intrinsic magnetic fields can align and not cancel each other out. Not surprisingly, these criteria are pretty difficult to fulfill, which is why there are only a limited number of suitable materials you can use when you're building a magnet.
Or you could just run a current through any electrical conductor and produce a magnetic field that way.
But hey, why does that work in the first place? Click here to go over to Veritasium.
So that's the other video you'll see later in grade 12 physics. But for now, that's that's a good rundown of magnetism, right? So the lodestone was found in nature and was magnetic and so on and so on, right? But basically, this is what led to compasses and so on. I'm going to jump through this because we've seen a lot of this already. But yeah, modern magnetism. Obviously, we're talking about the iron, cobalt, nickel, and you get the north and south pole and so on, right? And so the ferromagnetism that was described based on the half-filled outer shells is just, again, this is just what we saw in the video. We're only listing 3 here because the other one was basically not magnetic because of how it crystallizes. Yeah, so there's your ferromagnetic substances. We know what that means based on the video. Things that are paramagnetic, they increase the strength of a magnetic field only slightly if they're in the presence of a magnetic field, whereas these increase the strength of the magnetic field by a lot if they're in a magnetic field. And you have diamagnetic materials that will decrease the strength of a magnetic field a little bit if they're in a magnetic field. So each of these substances have what's called a magnetic permeability. So it gives the strength of the magnetic field as a multiple, right? So if you have the permeability or the magnetic permeability as a ratio, then you can get a multiplier, right? So when you divide the two substances values, you can get a multiplier. So for example, if you put pure iron inside of a coil of wire, the magnetic field you get will be 7,000 times as strong as if you didn't have the iron there, right? Because you're dividing those relative values. So pretty crazy. More easily accessible is like steel. If you put just an iron piece of a steel bolt or something between, you're still going to get 50 to 100 times stronger. But iron's obviously way better. So if you had this equation here is to do with the forces you get. So I was circling the wrong part there, got kind of messed up. But yeah, so the magnetic field with the core present versus the magnetic field without is that relative permeability. Anyways, so you could do calculations too with this. This isn't a major component of the course, but you can just get a multiple, right, for the forces. I found out what the forces become, so it's not really anything special. The domain theory is mentioned in the video as well. So not magnetic because everything's random, and very magnetic because things are lined up. But again, only possible if you have the half-filled shells and you have so on, all these different requirements. So magnetic poles, the law, obviously opposites attract and likes repel business. We are, I'm sure, familiar with. And so in drawing magnetic fields is pretty easy as well to visualize, right? You're looking at really looking at the direction a north would point. So it's repelling from the north over to the south. Canadians think of it as like a March break vacation, right? We're fleeing from the north and going to the south. So just be aware of magnetic field lines. If you put a compass anywhere near a magnet, it's the direction at any given spot. Point a little arrow in the direction the magnetic north of the compass would point. And that would repel away from the north into the south. And so if we're looking at things like two magnetic norths facing each other. We have repulsion away from a north, but repulsion away from a north, and you end up getting these like repelling magnetic field lines. You can actually sort of see repulsion in the magnetic field lines themselves. These lines are bending and get repelling off of each other, versus if you have magnetic attraction, you've got a north connecting to a south. It's like they connected the dots and are pulling together basically. So again, all of this stuff is actually caused by exchange particles called vector bosons and so on, but it's photons. Okay. So this view here is classical physics interpretation of electromagnetic fields, right? Where it's these fields and these lines and they're repelling and so on. The quantum mechanical analysis of this is to do with exchange of photons. And so we have these virtual photons going back and forth and so on. Sometimes we know real photons when an electromagnetic interaction involves real photons. So like if an atom absorbs energy, then it can release a real photon as light. The photons in magnetism are what's called virtual photons. So they always exist in pairs of photons, and they can only exist for a short amount of time. And so this is something that's looked at later in grade 12 physics, where we can measure the proportionality constant between the amount of energy that a photon has and the frequency it has. And also there's a link to how long the photon can exist as well. One of these is going to have time in it as a factor. So there's proportionality between the energy and the frequency, and between the momentum and the position. So the change in momentum and the change in position. I'm just showing this right now just for clear, like just to lead you into it later, but we'll certainly spend a lot more energy getting to know what that means. But the reality is these photons are real. It's a real thing. It's very weird. Yeah. So just quick here, showing like magnetic field lines. There's the repulsion, so the lines, bending and lining up beside each other, lines connecting. I just went and showed a bunch of different magnetic field lines for fun with iron filings and took pictures. So you have like, this is obviously like a north and a looks like yeah, those are the two norths by the looks of it. So repelling away, it's a little hard to tell there. Things like little disc magnets have this kind of weird look up to them when you look at them, and then when you look close up, you end up seeing that you have a bunch of vertical lines here, and it kind of has like the regular magnetic field from top to bottom when you stand it vertically. And so it's actually a north on one side of a flat face and a south on the other. Fridge magnets are bizarre as well. They have these like lines that show up, and it's actually a line of north, a line of south, a line of north, a line of south. And when you stick a fridge magnet to a fridge, then you've got this, from the end view, you've got a north, south, north, south, north, south, like this, north, south, and so on. And so then you put it against a steel surface, like a ferromagnetic surface, and then the field lines go through the metal and connect and become sort of bond as part of it. So the metal becomes part of that photon exchange that's going on. And so they get attracted. There's an attraction as a result of all that. We have like horseshoe magnet end to end. You just got like a north and a south here, and so on. So just showing like a bunch of different kinds of magnets for fun, but little magnetic round balls actually have like a north and a south somewhere along the line, because if you connect them all in order, they have a preferred kind of direction here. So you can see they're north, south, north, south. Can't tell when they're sitting individually, except that of course they're going to align kind of to north. So they all kind of align the same way, just sitting on a flat surface. And the 3D magnetic shape, I thought was just kind of neat when I looked at it. So I had the little balls on the bottom of the page and put iron filings on the top, and you could see the kind of the shape. And so if you pause, like right, maybe there's good, right? You've got like this, you can picture that field line. If you had enough iron filings, it would actually connect from there to there. So they're going out in all directions. and with only 2 balls or something like that, maybe you might even have been able to get it to like connect. So what am I at here? Yeah, and so just showing that because it's very physical and easy to show. Electric fields can be shown as well, but they're a little harder. But you can picture that being a repulsion, just like before, and an attraction. Very similar diagrams, right? And so there's applets that you can click on to show the kind of field patterns. So if you have a large charge, they show lots of field lines. If you have a small charge, they show not very many field lines, and so on. So there's links there, just you can click on and play around with. But you get the different shapes of electric fields from these different applets that can show you and help you visualize the invisible electric fields, even in situations like in this case here, you got a strong negative, let's say, like maybe, and then so it's like overpowering the other one, like and all sorts of different patterns. So you picture like a whole bunch of different patterns like that, and it's really hard to picture the electric fields, but these simulations make it much easier to be able to visualize those things. So yeah, that is the intro to magnetism and electromagnetic fields. I got rid of parts of it that I didn't like, so there's gaps in there and that, but I like the questions as they stand now, so there you go. Yeah. So thanks for watching. Like and subscribe to get this out to more physics people and for me if you don't mind, please. And of course, email me and put questions in the help section there for those that are actively part of this course. All right. Talk to you later.